Hello friends, myself Vatsal Patel, Assistant Professor in Civil Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, NAVSARI. Today we are going to discuss about control of groundwater in excavation. So moving towards the introduction, dewatering means the removal of excess water from the saturated soil. Dewatering is a necessary process when many construction it comes to the projects, particularly construction for the underground when comes for the large projects. So dewatering methods. Factors such as type of soil and the nature of construction site will all influence the which dewatering method will be best suited to the project. So there are many methods like sump and ditches, shallow well system, deep well system, well point system, vacuum method, cement grouting, chemical process, freezing process and electro-osmosis method. So first one is sumps and ditches. So you can see the diagram, plan and section of the sump and ditches method. So we are going to discuss about it. It is the simplest and most commonly used form of the dewatering. In this method, shallow pits called as sumps are dug along the periphery of the area and connected by the drains of semicircular in shape and 20 cm diameter. The water from the slope flow under a gravity and is collected in sumps from the which it is pumped out. Next is shallow well dewatering. A hole of 30 cm diameter or more is bored into the ground to a depth not more than 10 meter below the pump level. A strainer tube of 15 cm diameter is lowered in the borehole having a casing tube. A gravel filler is formed around the strainer tube, gradually removing the casing tube and simultaneously pouring the filter well so formed. The suction pipe from a number of such wells may be connected to a one common header connected to the pumping unit. So you can see the real life image or say typical layout of the shallow well point system. Next one is deep well dewatering or also known as the bored well system. This system is most suitable when the depth of excavation is more than 16 meter or where artesian well is present. In this 15 to 16 cm diameter hole is bored and a casing with a large screen is provided. A row of well point is frequently installed at the toe of the side slope of the deep excavation. A submersible pump is installed at the bottom of the well, of which the casing generally has a minimum diameter of 150 mm. The discharge pipe from the submersible pump of a number of adjacent wells are connected to a common delivery means. The water is raised from the well by a multi-stage pump. So we can see typical layout of deep well system in the image and pumps and various assembly used for it. Here is the schematic diagram of it. You can see all the process here. Next one is well point system. So the main component of well point system are well points, riser pipe, swinger arm, header pipe and pumps, which we can see in the image. So well point system. The well point system is perforated pipe 5 to 8 cm in diameter and 1 meter long covered by the cylindrical wire gauge screen known as strainer. Pipes are jetted in the ground 1 to 2 meter apart. Well point, then riser point, then swinger arm and then header. It is suitable for lowering water table by 5 to 6 meter in soil. So single well point system can be seen in the image. Different layer of water table and clay particles and sand particles we can see, and construction of it can be shown in the schematic diagram. This is the real life image of it. Next one is multi-stage well point system. So dewatering process of deep excavation and different stages we can see in the image. Multi-stage well point system is suitable for excavation up to 15 meter. So moving forward to it, when the water table is greater than 6 meter, this method will use. In this method, 2 or more row of well points are installed at a different elevation. In this method, wells are installed in 2 stages. In the first stage, water table lowered by 5 meter. If required, then third stage of well point can also be installed for the further lowering the water table. This method is useful for up to 50. So in each stage, water table is lowered down by 5 meter. So we can see schematic diagram of multi-well point system. Next, advantages. Installation is very rapid. The equipment is reasonably simple and cheap. As water is filtered while removing from the ground, soil particles are not washed away, hence there is no danger of subsidence of the surrounding ground. As the water is drawn away by the well points from the excavation, the sides of the excavation are stabilized and steeper side slope can be permitted. Disadvantages: single stage well point system is suitable for lowering water table by 5 to 6 meter only. For deeper excavation, whether water table is high to be lower down at a greater depth than 6 meter, multi-stage well point system is required. It is essential to continue pumping once it has been started until the excavation is completed. If it is stopped between, it may prove to be disastrous. In case the ground consisting of stiff clay, gravel or boulders, well points are installed in a drill hole, which increases the installation cost. Next one is vacuum system. We can see the schematic diagram of it in the image. So vacuum system, when draining is required for silt or clay which have size less than 0.05 mm, that time vacuum pump system will require. The process is as follow. The well points are driven and 25 cm dia is provided around the well point, installed in the ground by forcing a jet of water under sufficient pressure. The sand of medium to a coarse size is then forced into the hole rapidly as possible, and this sand forms the filter medium. In the uppermost 600 mm to 900 mm, an impervious material such as clay is stamped from the seal the upper portion. The pumping is then carried out by means of equipment capable of maintaining a vacuum in the well points and the surrounding filter. In this way, the pressure around the well point is reduced to a small fraction of the atmospheric pressure. The ground is acted upon by atmospheric pressure, thus the soil becomes consolidated under a pressure which is very nearly equal to the atmospheric. Next one is control of groundwater by grouting. In highly permeable cohesion-less soil, the safety of the side slope may be endangered through the application of sewage pumping. In such cases, especially if control of the groundwater is required permanently, the method of grouting can be used. The main idea is to insert a fine material or chemical around the excavation in order to reduce the hydraulic conductivity of the surrounding soil to a minimum. In other words, we can say that the grouting process creates an almost impervious curtain around the excavation. The grouting is conducted using movable pipe with the holes. The grout material is injected under pressure as it flows outside the pipes through the holes to fill the voids of the surrounding soil. The material used for grouting may be clay, cement or special chemical compound. So we can see schematic diagram of the grouting control groundwater. Next one is cement grouting. We can see plan and section of grouting of soft soil using cement grouting. So cement grouting can be seen by schematic diagram, and jet grouting is also shown in the image. So cement grouting. The material commonly used for grout includes cement and water, cement, rockfort and water, cement, clay and water, cement, clay, sand and water, asphalt, clay and water, chemical grouting. The desirable property of the chemical grout: it must be able to modify the properties of soil as desired. It may either increase the strength or decrease the permeability of soil. It must be cheap, non-toxic, non-explosive. It must be in the form of liquid with low viscosity so that it can be readily placed in the soil. It must be non-corrosive so that it can be handled with common pumps and piping. It must be possible to control the gel time by suitable means. So we can see that chemical grouting is inserted by using high pressure hydraulic pump, and pressure gauge is monitored during the whole process. Next, chemical grouting. Inorganic chemicals which are used for the chemical grouting are sodium silicate, calcium chloride, lignochrome, lignosulfate. They are called silicate grouts. They are cheaper. And organic chemicals like epoxy resin, polyester resin, they are also called resin grouts. They possess advantages of low viscosity, precise control of gel time and high strength. Next one is freezing process. Soil that will not drain using conventional method, typically a ground freezing system, consists of an array of freeze pipes that are installed into the ground around the perimeter of the excavation, usually in the circular pattern. A supermodel brain solution is Briney solution is formed through a freeze the pipe, which freezes the water-bearing soils around the pipes to create a frozen wall. Extreme care must be taken to make sure that the freeze is complete, because the groundwater seepage through the wall or from below the excavation depth will have a sliding effect. So we can see the freezing process in the image using mobile freeze plant. This is also second image of it. Next one is ground freezing. So moving towards its procedure, a refrigerator plant of required installed near the site of work. The large pipe of 100 mm to 150 mm diameter are used. The distance between these pipes are about 1 meter to 1.50 meter. The pipes are closed at the bottom. The small pipe of 25 mm to 50 mm diameter are inserted into the large pipes open at the bottom. The cold liquid at a temperature of about minus 23 degrees Celsius to minus 30 degrees Celsius is then circulated through the circuit. The liquid comes through the small pipe and goes up through the large pipe. This causes the ground to freeze around the pipes. Next one is electro-osmosis process. We can see schematic diagram of it. So electro-osmosis process. This method is used for fine-grained cohesive soil such as clay, which can be drained or stabilized using electric current. The method was developed by L. Casagrande in 1952. If direct current is passed between two electrodes driven into the natural soil mass, the soil water will travel from positive electrode, so anode, to the negative electrode, cathode. The cathode is made in the form of WELLPOINT or metal tube for pumping out the seeping from the WELLPOINT, or a metal tube for pumping out the seeping water. A steel rod, a pipe, or steel piling of excavation can serve as the cathode. The arrangement of electrode is done in such a way that the natural direction of flow of water is reversed away from the excavation, thereby increasing the strength of the soil and stability of the slope. The potentials generally used in the process are from 40 to 180 volts with electrode spacing of 4 to 5 meters. Next one is vibroflotation process. The vibrofloat is inserted into the ground and typically can be used to improve soil up to depth of 150 feet. Vibroflotation utilizes water and the mechanical vibration of the vibrofloat to move the particles into a denser state. Typical radial distances affected range from 5 to 15 feet are used. The vibrofloat is suspended from a crane and sets on the surface of the ground. That is to be improved. To penetrate the material, the bottom jet is activated and the vibration begins. The water saturates the material to create a quicksand condition, for example temporarily liquefying the material, which allows the vibrofloat to sink to the desired depth of the improvement. At that point, the bottom jet is stopped and the water is transferred to the upper jet. This is done to create a saturated environment surrounding the vibrofloat, thereby enhancing the compaction of the material. The vibrofloat remains at the desired depth of improvement until the material reaches the adequate density. The density of the soil is measured by using power input via the electric current or hydraulic pressure as an index. As the material efficiencies, the vibrofloat requires more power to continue vibrating, at which point pressure gauge displays a peak in required power. Once this point is reached, the vibrofloat is raised one lift, generally ranging from 1 to 3 feet, and compaction ensues until the peak amperage or the hydraulic pressure is reached once again. So we can see schematic diagram of all the process, all the stages of it. Advantages. The vibroflotation process can offer the following benefits. When the process is done properly, it will reduce the possibility of differential settlement that will improve the foundation condition of the proposed structure. It is the fastest and easiest way to improve soil when the bottom layer of the soil will not provide a good load bearing capacity. It is a great technology to improve harbor bottoms. On a cost relation standpoint, it helps improve thousands of cubic meter per day. It is faster than piling. It can be done around the existing structure without damaging them. It does not harm the environment. It improves the soil strata using its own characteristics. No excavation are needed, reducing the hazards, contamination of the soils and hauling material out from the site. Suitability of different methods of groundwater condition. So methods and its suitability is shown in the table. So SUMPS and ditches are suitable for shallow excavation in coarse grain soil. Well point system is suitable for lowering water table by 5 to 6 meter in soil. Bore well system are used for coarse grain soil and depth of excavation more than 16 meter. Vacuum method is used for draining silty sand and fine sand. Cement grouting for the coarse material like rock with cracks. Freezing process suitable for the excavation in waterlogged soil, and electro-osmosis process is suitable for the fine grained cohesive soil such as clay. So here I end my session. Thank you all of you.